Hi everyone, I'm Shuyuan Chen from Peking University, and my topic is about paraffin-coated cells. And I will introduce some recent progress in this year. Here's the outline. And coated vapor cells have been widely used in many applications, like unshielded biomagnetic detection using OPM sensors, and searching for dark matter using global network of optical magnetometers for exotic physics. As well as benefiting the light storage time in quantum information. So among the anti-relaxation coatings for coated vapor cells, OTS, alkenes, and paraffin are the most frequently used materials. And either of OTS or alkenes has serious defects, respectively at maximum bounce times and melting temperature. So in the applications of optical magnetometers, paraffin becomes the most attractive material for its high melting temperature and high anti-relaxation performance. So here we show coherence lifetime of 17 seconds in paraffin-coated cells with its maximum bounce times up to 2 times 10 to the 5 and melting temperature up to 70 degrees Celsius. So in the application scenarios for OPM, the standard quantum limit is limited by the product of vapor density and the relaxation time. So which are the core issues in the view of OPM. So to optimize the sensitivity limit, we need either increase vapor density or prolong the relaxation time. First, there are two major means of increasing vapor density. One is light-induced atomic absorption, which we call the LIAD, without cell heating. The other way is heating the vapor cell to high-temperature dense vapor. As for the relaxation time, we choose T2 instead of we choose T1 instead of T2 as our characteristic relaxation time in the standard quantum limit expression, as it reflects the potential limit of without the effects of spin exchange or magnetic field gradient. So to prolong the longitudinal relaxation time, we need firstly improve the coating performance. There are numerous factors influencing the performance, like chemical bond, absorption energy, and interactions with alkali metal atoms. Another way to prolong T1 is to suppress the reservoir effect. As we know, a coated vapor cell is consisted of a coated cell body and an uncoated cell tail, which serves as the alkali reservoir. So it is a relaxation due to the cell body and cell tail vapor exchange. And this type of suppression is quite effective in the coated vapor cells with a high coating performance. So actually, what we focus on is the relaxation behaviors in dense vapor cells and high temperature cell performance. And how to suppress the reservoir effect? Previous work reported the design of a glass bullet at the capillary between the cell body and the reservoir. However, this did not result in relaxation time increase in practice because of its process consistency and difficulty. So here, in our study, we designed a coating lock by cell ripening instead of glass bullet to effectively suppress the reservoir effect. And for paraffin-coated cell, T1 has a remarkable increase after locking. After this, it is necessary to give a precise and appropriate performance characterization of these vapor cells, especially T1 and vapor density. So as for the measuring methods, we use linear absorption fitting methods in atomic density matrix package to measure the vapor density, where we sweep the single beam frequency to get the absorption lines. As for T1 measurement, we use modified relaxation in the dark scheme, where the pump and probe beams are propagating along the magnetic field direction. And we first pump on to generate steady orientation and then pump off to let the spin polarization relax freely in the dark. Then we apply a tree exponential fitting function to fit the curve. And we choose the slowest characteristic time TS as our longitudinal relaxation time T1. And here we show the 17-second T1 measured at 61 degrees Celsius. After that, we also design an on-site monitoring system to monitor T1 and vapor density at the same time during the entire cell ripening process. It is special because we use the lens to collimate the beams, and The water-based methods ensures a uniform heating and performance monitoring during the entire cell ripening process. We also use linear absorption fitting method and modified relaxation in the dark scheme to measure the T1 and vapor density as we mentioned before in this system. Utilizing such ultra-long T1, we can realize some interesting effects like spin bistability and spontaneous polarization in paraffin-coated cells. One of the prominent features of this bistability is the steady state polarization depends completely on the initial state. We use cesium D1 line FMU equals 3 to FM equals 4 for our linearly polarized optical pumping. And because its special transition probabilities induces the final spin bistability. So when the spin exchange rate and the optical pumping rate is much larger than the longitudinal relaxation rate, the atomic spin polarization grows parallelly or antiparallelly to the quantum axis, which corresponds to the directions of the two stress states. So here's the paradox of observing spin bistability and spontaneous polarization. And we apply 3 identical beams, A, B, and C. Preparing beam A is circularly polarized and provides initial polarization. Driving beam B is linear polarized and induces spontaneous polarization towards either of the stress states. And we can obtain the polarization evolution information from the optical rotation signal of probe beam C. So in time domain, we design the preparing driving relaxation stages to observe the bistable states S1 and S2. So we design different initial polarization signs by controlling the circularity of the preparing beam A. And then in the driving stage, the atomic spin polarization grows towards the corresponding polarization direction according to the initial polarization signs. So it is driven by the driving beam B. And in the time domain, in tau 2 to tau 3 and tau 5 to tau 6, we let spin polarization relaxation in the dark for the next preparing stage. Another feature of this bistability is the hysteresis loop with pump circularity. So initially in the time evolution observation, we use linearly polarized driving beam B. So here we change the circularity of this beam and make a comparison between the two paraffin-coated cells. Every point in this graph is obtained as a steady state result. So paraffin-coated cell 1 with a coating lock has a T1 of 8 seconds at room temperature and is satisfied with the bistability generating conditions which we mentioned before. And the paraffin-coated cell 2 without a coating lock has a T1 of 1 second at room temperature. And the result shows the hysteresis loop only appears in cell 1. So it shows the vital role played by T1 prolongation and the coating lock design. After reaching ultra-long T1 in paraffin-coated cells, it is necessary to increase T2 for the applications of OPM. So here we realize a minimum line width of 0.36 Hz by light narrowing in MX scheme instead of FID scheme at room temperature. So similarly, we also use 2 paraffin-coated cells, one cell A without a coating lock and cell B with a coating lock. So locked cell B, we call it locked cell B. Locked cell B with a longer T1 has a smaller minimum line width. Besides, as the pump power increases from 0, the population increase in the stress states narrows the overall line width as this part no longer contributes to the spin exchange relaxation. However, for unlocked cell A, the light narrowing disappears at 47 degrees Celsius as vapor density increase induces a stronger radiation trapping effect, as marked in gray. So radiation trapping dominates the high temperature range, but for our locked cell B, we can observe light narrowing over 30 degrees Celsius range. And the overall line width hardly changes with the cell temperatures. So this kind of line width differences can be reflected in the vapor density variation when we heat the vapor cell from 27 to 59 degrees Celsius. So for for analog cell A, vapor density has a 20-fold increase, and the minimum line width has a 9-fold increase, which is just what we expected. But for locked cell B, we have reached a vapor density stabilization over the broad temperature range. So as for the system robustness, we use, sorry, this paragraph maybe shows a little mistakes. So as for the system robustness, we use zero crossing slope KC of the magnetic resonance quadrature component, as it provides a means of evaluating the sensitivity limit of the locked cell-based OPM sensor. So after optimizing the parameters of pump power and the radio frequency field, we can plot the KC variation with cell temperatures. And for unlocked cell A, the KC varies by 382%. But for locked cell B, the variation is only 10.5%. And besides, the largest KC appears at room temperature for locked cell B. So for as for the temperature insensitivity for OPM system, we start with the vapor density stabilization and then transforms into slope stabilization, and finally has a chance to achieving OPM sensitivity robustness. Sorry, this slide is a little mistakes. So based on the magnetic resonance signals, we can analyze the noise limit of this locked cell-based OPM sensor. So the photon noise limit is estimated as about 0.2 femtotesla per square root hertz, and spin projection noise is estimated as about 1.1 femtotesla per square root hertz. So based on these paraffin-coated cells with a coating lock, we preliminarily design engineering Bell-Bloom-based OPM sensor with a single beam path. So the pump and probe beams become one through the fiber coupler, and compared with the two beam scheme, the dead zones are reduced from 2 directions to 1 direction. And besides, it is also conducive for the subsequent miniaturization design. Utilizing such two identical OPM sensors, we can obtain the different results of noise spectral density at 50,000 nanotesla. We initially get a noise floor of 60 femtotesla per square root hertz at 10 hertz. So compared with noise limit, the spin projection noise limit and the photon noise limit analyzed before, the noise floor in practice is limited by current source noise and is susceptible by magnetic field gradient. So we can deduct that this type of vapor cells with ultra narrow line width is better used in environments like NEDM experiments, where the gradient is very small. Also, the line width broadening reflects the gradient. So finally, let's take a look at the future of these paraffin-coated cells with a coating lock. Firstly, we plan to do more actual extreme temperature environmental testing and explore more temperature insensitivity application scenarios, not only in OPMs, but also in other sensors like atomic clocks, because temperature insensitivity is a broad range. So secondly, we are also interested in vapor density increase within coated cells with a coating lock. For example, we can use light-induced atomic desorption for observing this phenomenon. Besides, paraffin-coated cells with long coherence lifetime could benefit the storage time for quantum information, which we mentioned before. Furthermore, we intend to explore other coating material-based coating lock. Maybe we can use oil baths instead of water baths because of the higher melting temperature of the other coating materials. So this is a summary, and thanks for listening, and welcome any open questions.